Does your free body diagram look like this? So what is a free body diagram? It has every force acting on our block, right? That's the free body diagram for the block. It has every force acting on the block. So we could now come up with a list for our total work done. Because why do we need the total work done? Because we're going to equate that to change in kinetic energy. And that has to equal change in kinetic energy. We already know that the normal force and the weight do no work. So we have the work done by friction added to the work done by F is going to be final kinetic energy minus initial kinetic energy. So the work done by friction and what do we get? Is that right? 1/2 m v final squared minus v initial squared. Final was 3 meters per second, initial was 1. And what is the work done by the force was 100 joules, right? So this is 8 times 5 is 40, is that right? Did I get it right? We know it has to be negative. Friction is opposing the motion of the block, right? So we know we're going to get a cosine 180 in there, right? Friction and delta x are in opposite directions. Anybody check my algebra? Are we good? Okay. So we know the work done by friction, and we know work is force dot product with displacement. And what is the force of friction? Mu times the normal force. Okay, friction force multiplied by the displacement multiplied by cosine of 180. That's the work done by the friction force. We know that has to be negative 60, so we can start plugging some things in here. This is going to be, what is this going to be? Normal force is just equal to the weight, right? Which is, what is that going to be? Can we just use 10 for G, or? It's 10 kilograms. Five meters, right? And what do we get? The minus signs go away. What do we get? .12. What are the units on that? It's unitless. Yes, correct. No units. So we good? So you see how we can sort of work around with friction. Work around now with energy and find some things in different ways, right? We have a different tool now for getting us sort of to the same result. So with, right before energy, what would we have done? We would have said sum of the forces equals ma, come up with an acceleration, maybe used our kinematics equations to figure out something here. Or maybe we would have used our kinematics equations to find the acceleration, right? If we were given v initial and v final in the distance, maybe we would have used our kinematics equations to find the acceleration. Then we use our accelerations with F equals ma to figure out what the force of friction had to be, and then find mu sub k. So we've gone now, we have a different way of getting to the same answer. Maybe it was easier. Most of the time it's easier to use energy. So, and the other thing with energy is that we're not constrained to constant acceleration, right? If we use kinematics equations, the acceleration has to be constant. In this case it was, so we could have used it. But we could have had some other thing in here that caused the non-constant acceleration, like a spring. Right? We haven't talked about springs yet, but we will. Springs cause a non-constant acceleration. The force changes with distance. So you cannot use kinematics equations anymore to find the acceleration. You have to use some other technique, energy.